Okay, we've got 1:30, so why don't we get started? Good afternoon, research methods. That's pretty good. A little better. Good afternoon, research methods? Okay, now it looks like we're all set. Welcome to Tuesday of week number 8. And this is great news because we know that if today's Tuesday, tomorrow's Wednesday, and we know what that means. Yay! There goes Natalie. Natalie's going crazy because we're going to have a quiz tomorrow. It's hard to maintain one's excitement and keep it under control. So I realize that people are all jazzed up about that. So why don't we play to that and just remind you what's available on the quiz tomorrow. So out on the S drive and out on Blackboard also, we have this information. Okay, and a lot of this is review for us. We know it's worth only 50 points. You'll be given a formula sheet. Some of the formulas that you'll be given, I'll be giving you a formula for the chi-square test. You'll probably have memorized some of those, but I'll give you the chi-square formulas for the goodness of fit, and also for the test of independence. I'll also give you the formula for the Pearson R. That'll be another one of the items that we've done in recent weeks that'll finally make its way onto one of our computer quizzes. I think we'll do it this way. You can see that the tests that we were thinking about doing were shown in green. I think I'm not going to push us to do an independent samples t-test. So we'll take that off of this time, and we'll put that onto the next one. So I'll take that down right here. Okay. So if you are prepared to do an independent samples t-test, you are ahead of the game. We'll eventually be testing you on that, but not tomorrow. Okay, so no t-test tomorrow. But we will have the chi-square test, as I've mentioned, Pearson R, also z-scores. This is something that you've done in the past. And we can revisit these scores if we need to. Okay, you can practice tonight if you'd like. You want to make sure that you can do these different kinds of things, the Pearson R, the chi-square tests, and so forth on SPSS and also in Excel. Okay, please go ahead.
So we're not going to go over the packet?
We are going to do that today, but it won't be on for tomorrow, just in case people need a little bit more practice. So we'll be doing t-tests today in just a little while, but I hate to introduce something and then sometimes we're running a little bit short on time and then it's on the quiz tomorrow. It doesn't seem fair to you. So we will get 2 t-tests today, but we will not hold you responsible for those tomorrow. Okay? All right. Any other questions or comments about what's on the quiz? You've done these before? Okay, real good. Why don't we put that one away? Okay. All right. And what I thought I'd do is just refresh our memories a little bit for some things that we've learned, but I thought I might set the stage this way for tomorrow's quiz. And I thought I'd review a couple of concepts before we get into some actual computation, just because I thought yesterday we were a little bit rusty in trying to understand some of these distributions and so forth, which we had seen once before, but I thought I'd offer this to you. The phrase evaluate the null hypothesis, you might see that from time to time. That means to decide whether or not to reject HO. So for about a week or more, we've been evaluating hypotheses. We had an entire session on hypothesis testing, and we're going to be spending the rest of the semester on some variety of hypothesis testing. So when you see evaluate the null hypothesis, that means that we have to come to a decision. Reject or retain the null hypothesis. Here's one of our mantras. When sig is less than 0.05, we reject. Can we all say that together? When sig is less than 0.05, we reject. Okay? So that rule pertains to HO and also to parametric tests. We have these other kinds of assumptions and so forth. But for right now, we're only going to be looking at the sig value with respect to HO. For the chi-square test of independence, that evaluates the association among 2 or more nominal variables. What was our synonym for nominal variables? Categorical variables, right? Okay, these are qualitative variables. Goodness of fit evaluates a single variable's compliance to expected proportions. So we had quarters yesterday. We were talking about 1/4 of the sample valuing one particular kind of reason for selecting courses, another fourth valued a different reason, a third fourth evaluated preferred another reason for selecting courses and so forth. So that was goodness of fit. We only have one variable here. And then t-tests, which we won't do for tomorrow, although we will be talking about them today, but they won't be on tomorrow's exam. These are going to be evaluating typically 2 means. There is a variation called a one-sample t-test that is even simpler than that. So this is really about means, and so it's parametric. The chi-square is going to be non-parametric, no means involved. Okay, questions on any of that? Okay, I think that's Good. Why don't I go back and just remind us of something that I think we were stumbling over yesterday. We got to the part where we were about to make a rejection or retention of the null hypothesis, and I got the sense that people were a little bit confused about how to interpret values on this. So before we get to the chi-square distribution, let's return to something that's a little bit more familiar, and we'll see a connection that goes here. We talked about the power of the Gaussian distribution when we had our conversation on z-scores, and we said that these were really powerful because they allow us to connect very different ideas, seemingly unrelated ideas that we can basically compare apples to oranges by way of z-scores. And what was nice about the Gaussian was that all Gaussians have these kinds of proportions. And if we're at something like the second z-score above the mean, then that would mean that we're at the 98th percentile of that distribution. Who remembers doing that, first of all? Okay? And who finds that clear? Okay, really good. Okay, so the point about that is even for this simple distribution, we can describe a particular point on the x-axis with respect to its z-score, for example, positive 2 on the z-score, and its percentile rank would be, I'll let you yell it out, the percentile rank associated with the 2 z-score, 98th percentile. So two different ways of saying the same thing, percentiles or these z-scores. One more, we can even say maybe there's a third way of talking about this. If we have a particular psychological variable of interest, let's say it's IQ, okay, and I'll give you a sample IQ. Let's take an IQ of, say, 115. Okay, let's say that somebody has an IQ of 115. Can you give me two other ways of expressing that IQ based on this picture? So I'm giving you one way to express that IQ in raw IQ points, 115. Two other ways to do it? Anybody want to help us out with that? Okay, yeah, thanks. Has a z-score of positive 1, and can you just remind us how you got that, Kip?
It's 15, which is the standard deviation.
Okay. Okay, really good. And then can you help us out with the remaining way of describing that?
Would that be I'm not sure.
Okay, that's all right. You got us half the way there. So we can talk about the raw IQ score was 115. The z-score puts us at positive 1. There's one other way of doing it. Is that a hand, Brittany, or just, oh, yours, okay. One other way of doing it, we said it a moment ago. We can use percentages. Yeah, thanks, Mira.
I think it's 74 or 74%.
Okay, you're getting close. You're within 10. The 84th percentile. Okay, so Mira and Jenna, I think, are converging on that. I'm going to go with Jenna. Can you just remind us how you got to the 84th percentile?
Well, if it's at the z-score of 1, it's everything at or below.
Uh-huh.
And so then adding up those percentages, that's the 84th.
Okay, right. So this would be the 84th percentile. Here's the first 50. That cuts the distribution in half. 50-50. Half is that way, half is that way. We're going to add an additional 34 because Kip correctly told us that a IQ score of 115 is one standard deviation above the mean, which is to say one z-score above the mean. That puts us at z-score positive 1. We're at the 84th percentile, and our IQ score is 115. That's the raw score. That's the z-score. That's the percentile rank. Who's okay with all of that? Okay. Any questions about that? Please, go ahead.
Is this like z-score of 1 being 84%, or the 84th percentile? Is that like universal?
Yes. That's as universal as the Pythagorean theorem is for right triangles. Okay? Yep. Good question. Okay, people are all right with that? Same kind of a thing, by the way, for lots of other known distributions. By the way, one such known distribution is the chi-square distribution. It's a little bit different in the sense that that one is symmetric, this one is skewed, this has a positive skew, but we can still say that for a given known chi-square distribution, and we know them by their degrees of freedom, we can pick a particular cutoff value, and we can say that we have basically that same score. This time it would be a chi-square score rather than a z-score, and that's going to have some kind of corresponding percentile rank. Who's following that? Okay? And typically we're interested in what's a typical score versus what's an extreme score, what's unlikely to occur just by chance. And that brings us to our next slide. The issue that I think some of us were struggling with yesterday was another review issue, and this was on 10.8, and it was slide number 12. Who remembers seeing this slide at any point, right? From 10.8, we talked about type 1 errors and type 2 errors, false positives and false negatives in hypothesis testing. And the false positives are indexed by this alpha, the probability of making a type 1 error. And that's what occurs way out here in this rejection region, as we've talked about before. So we're perfectly willing to reject the null hypothesis, but only if we have a really, really low probability of getting such a high value by chance. Okay? So if we're out here into the extreme, we say that we have enough evidence, we've met the burden to reject the null hypothesis. The null hypothesis being typically that there's no association between the variables or that there's no effect of our independent variable. Okay? So that's all review. We had done all of that stuff, and we're just trying to pull all that together as we engage in hypothesis testing. Let me see if there are any questions about that portion of our review. And we'll do one more example. Okay, maybe we'll do the one thing that we haven't done so far that will still be on tomorrow's test. There's one little bit that we haven't done with chi-square, and that's the chi-square test for the goodness of fit inside of SPSS. We did a really nice example yesterday by Excel, but we hadn't done it yesterday by way of SPSS. So this will only take a moment, but if you'll join me, please, by going out to SPSS, and why don't we use our data set? We'll use the NESI data set for the Denison students. And we've opened that maybe 2 or 3 times already. But I'll let you open SPSS and then navigate out. You want to pick up a data file. You say File, Open Data. You can navigate out to our S drive inside of the practice folder, and I'll point to what that looks like. And then there's a subfolder called NSSE, the National Survey of Student Engagement, and we had a whole bunch of Denisonians take this. So we'll open that one up. You can go inside of that folder, and we've done this one a couple of times. Open that, and then we'll get a full data set, and we can look at variable view or data view. Show of hands, how many people have that up? And Maddie has a question?
Yeah, your name's coming up.
Okay, are you on the S drive?
Yeah.
Okay. Okay. Maddie, I wonder if for the moment you can sign out and sign back in. Sorry about that, okay? All right, how many other folks have that one up? Okay, is that working for us? Okay. Now, yesterday I handed out a sheet that has the steps that we would be using for the chi-square test for the goodness of fit, but we didn't get the chance to use that yesterday. So why don't we try and do this? And remember that the chi-square test for the goodness of fit allows us to classify data along one dimension of variability. And the example that we had given yesterday was course selection, and we had 4 different possibilities and so forth. Now why don't we go into this data set, and I hope you'll join me in variable view. Okay? So you'll click over on the second tab, and we'll come down and we'll take a look at some of the variables that we've seen before. I wonder if we might do something like, how about frat sorrow? Okay? So that's the 88th variable. And this is, are you a member of a social fraternity or sorority, the 88th variable. Can somebody tell me how this variable is coded? What are the possible values that we have for this thing? We'll let you plug away on that. Okay, thanks, Katie.
1 is no and 2 is yes.
Okay, 1 is no and 2 is yes. It's a pretty easy categorical variable. Okay, so why don't we see if we can ask a question that we might be able to answer by using the chi-square test of goodness of fit on this particular variable. We'll take maybe a simple example here and then a variation on that simple example. So we might ask, for example, is it the case that people are equally likely to be associated with a fraternity sorority versus not associated with fraternity sorority? So that is to say, we have about as many yeses as we do nos. We'd call this the even-Steven hypothesis, that we're about 50-50 on whether we're saying yes to this or no to this across the sample that's being surveyed. Who's following that? The 50-50 bit? Okay. And we can go with something other than 50-50 in a few moments. Why don't we just start out that way? Okay. Does anybody want to help us with how we get this analysis going? Yeah, thanks. Okay, analyze. Okay, we might do descriptive statistics, and that's what we frequently do for chi-square. I wonder, and that was actually a really good start. There's another way to get into this for the test of goodness of fit. Okay, so we're going to go analyze, and then we're going to go down to non-parametric test, and we'll go to legacy, and I'll pause that far, and I'll let you click on chi-square. Meg also had a hand up. Was that just to direct us?
Yeah.
Okay, thank you, right? Okay, so it's a little bit confusing there. I wish it were the case, and it would have been very intuitive for SPSS to arrange all chi-squares together, which is why Jenna had a beautifully intuitive answer, and there's actually no good reason why SPSS arranged this the way they did. But they happen to have arranged it this way, so we're going to go to non-parametric tests, legacy dialogues, and chi-square. How many people got that far? Okay, that's great. I'm going to go that far also, and I'll click on chi-square, and I get this kind of a this kind of a presentation. And what I'll ask you to do is dial down into your variables, and you might want to bring it all the way down or nearly so. And then we'll click on, are you a member of a social fraternity? You might see some or all of that, and we'll slide that one over. That becomes our test variable for our chi-square, where the null hypothesis is that in the population, answering yes and no are equally likely on this question, which is, are you a member of a social fraternity or sorority? Okay. Notice what it defaults to. It defaults to all categories are equal. How many people are able to see that? Defaults to that, all categories are equal. Now we could click on some alternative. We could click on values and we could put in different kinds of values here, but why don't we just go along with this? So we'll go with all variables are equal, and we'll click OK. Okay. Then we'll get some kind of output here. And I'll let you look at the output for a moment, and then I'll let you see if you can try to interpret this for us. What kinds of things is the output telling us as we evaluate our null hypothesis? Anybody want to help us out with that? Okay, thanks, Mira. That's a perfect answer. We can reject null hypothesis. So first, how many people see where she's coming from there? Okay, how many people are not entirely sure where she's coming from? Okay, thank you for being honest. Some of us are not entirely sure. Mira, that was right on the money. Can you tell us how you got to that conclusion?
The sig number is less than 0.05.
Okay, the sig number is less than 0.05. Okay, so remember that we have this criterion alpha level, okay, and then we have an observed alpha level, and we reject HO if the observed alpha level is 0.05. And here I'll make a little note that the observed alpha level is also called the sig, a little bit counterintuitively inside of SPSS. Okay, so we have that value, okay? And that's actually quite a bit less than 0.05, right? If we could have more digits of precision, it might be 0.00004, but it didn't even make it to 0.001 with rounding, okay? So we could say that we're going to reject the null hypothesis in that case. Of the folks who found that a little bit confusing, did that work for you now? How many people are okay with that? Okay, if you are okay with that, can you raise your hand really, really high so I can see who's on board and who's not? And I didn't, okay, that works for you, okay, real good. All right, so now we know at least one thing, that we have a rejected null hypothesis. Can somebody tell me about the value of the statistic itself? The value of the chi-square statistic itself. What is that? So we know that the alpha level, which is the asymptotic sig, is less than 0.05. The value of the chi-square statistic is, thank you, Kip, 71.111, right? Okay, so that's where that is. So let's see if we can now put that into some kind of perspective. Here's the chi-square distribution, and in this particular case, we have 1 degree of freedom. And we'll unpack that just for a moment. Why do we have 1 degree of freedom? Anybody have a notion about that? Thanks, Mira. Oh, is that just a hand mirror? Or that?
I'm not sure.
Okay, you're allowed to cheat and look on the handout that you're going to have tomorrow. Go ahead, Jenna.
Well, we've got yes and no, and degrees of freedom is the...
That's exactly right. That's right. So we have how many categories? 2. Yes or no are the possible responses, the possible permissible responses on this question. So you can only land in one of 2 categories. And the degrees of freedom formula that you have on your sheet would indicate that it's the number of columns that you might have, which means the number of categories minus 1. 2 minus 1 is 1. Who's okay with that? Okay? So we have this positively skewed distribution, that's a chi-square distribution. Specifically, it's the particular chi-square in the family of chi-squares. It's the particular chi-square that has 1 degree of freedom. Okay? And we have a chi-square value that equals 71.11, and that presumably has exceeded the critical value of whatever that might be, and it's way out here somewhere, 71.1. And the probability of getting that by chance is really, really low. It's, in fact, so low that we can't measure it beyond 0, 0, 0. You know, it might be that there's 1 chance in 10,000 or 1 chance in 20,000 or something like that of getting a chi-square value that big or bigger just by chance. So that's a very extreme score. We could be making an error by rejecting the null hypothesis, but the probability of making that error is less than 1 chance in 1,000. That's our alpha level. Who's following all that? Okay. So why don't we just end with this? We'll see if we can begin to write on the board what the folks at the American Psychological Association would like us to say about this kind of analysis. They would like us to report the following, and please take this down with me, that we have a chi-square test. Okay? So now we're reporting to the audience what it is that we've done statistically. We could have run maybe a z-test or some other kind of a test. We actually ran a chi-square test. Okay? And we had 1 degree of freedom, comma. We might want to put in our n. Can somebody tell us how many people we had in this particular analysis? 360, really good, okay? So good to be, and we could say something like this, n equals 360. I'll put that off. Our observed value is 71.111. And the p-value is less than 0.001. That's typically how we would say it. Right here it says that p is 0, 0, 0, but it's actually never really 0. It's just that we ran out of real estate, so to speak, on this one. So we can say that the probability of getting that chi-square by chance is less than 1 chance in 1,000. That's as far as we can measure it. If we had more digits of precision, we could offer more digits over here, but it's less than 0.001. Okay? So that tells the APA audience, the American Psychological Association audience, what we did, how many people we had, what kind of chi-square were we dealing with. It was the chi-square that has 1 degree of freedom. What did we empirically observe? And then what's the probability of getting that kind of a outcome just by chance? And we could say one more thing if we want here. We could say reject HO. Okay? So we're rejecting the hypothesis that the yes and no responses occurred equally in our particular sample. Okay? They were actually not equal. Please, thank you.
What does the n stand for again?
Where does the which one?
N.
N is the number of people. Okay? Yep, we'll see that in many, many cases. Thank you for the question. N is the number of people. We'll go with Marin, and then we'll go with Katie.
What is the p?
The p is the probability of getting this by chance. You can also think of this as our asymptotic sig value. Okay? It's the probability of a type 1 error. So we're rejecting the null hypothesis. We're going to pull that fire alarm and say, we think we've got something here. And we might be doing that in error. Okay? If we're making an error, it would be a type 1 error. But the probability of being a type 1 error is less than 1 chance in 1,000. Why? Because distributions all work the same way. Right? And we know that if we're out at 71.111, there's only this tiny fraction of the population that's beyond that. Okay, and Katie had a question.
Wait, so I thought that it was the p had to be less than 0.05.
5. And 0 turns out to be less than 0.05.
Yeah, so when you write 0.05.
Okay, so actually what we observed was that our p-value is less than 0.05, but we can say even more than that, Katie. We can say our p-value is not only less than 0.05, it's less than 0.001. We have the evidence empirically to make that claim. It's a stronger claim, but we have that evidence. Does that work for you?
Yeah.
Okay. Yes.
And I have
Yeah.
another-
Yes, please. Thank you.
I'm still confused on how we analyze the chi-square. Like what do you how do you know that the 71? What the 71.111 means?
Yes, right. How do we know? Well, all we know is that's what we have observed empirically, right? And we know that it must be somewhere to the right of this critical value. Okay. So we're reporting to our audience what we observed. If that is to the right of the critical value, then its alpha level must be less than 0.05 because here 5% of the population is that way, 95% of the population is that way. One of the things SPSS doesn't do for us is it doesn't give us that critical value, that value that we'd actually have to beat here, but I think you can get it. As a matter of fact, that might be a good test question. Let's see if you can use Excel. I'll let you minimize. We're really done with SPSS for today. Can you use Excel to figure out really the answer to Katie's excellent question, which is what would the critical value be for a chi-square distribution that has degrees of freedom of 1, and we're testing at the 0.05 alpha level. Okay? We did this yesterday. We'll see if you can connect things for us yesterday. Some of you might even remember the number, but can you use Excel to come up with a critical value that we would have to exceed to reject the null hypothesis? So we'll give you a moment to do that in Excel. And while you're doing that, I'm going to put something else up. I'm going to go back to here. Okay, Brittany's got something.
No, actually. No, because I wasn't here yesterday, so if we get explanation of exactly how to do it.
Yes, it is, as soon as we get a student to tell us that. So we had a whole bunch of students tell us that. And I think Marin's got something that will go to Jenna, too. Do you have an answer for us?
Yeah. Is it 3.84?
Okay, what does Jenna think? What does everybody else think? 3.84? How many people came to that answer? If you can raise your hand, that sounds good to me. 3.84. So let's go back over to here. In this case, the critical value, according to Marin and according to Jenna, is 3.84, and that's what I think I remember from yesterday. I wonder if Marin or Jenna can share with us how you came to that number, and this will be particularly helpful to Brittany. So this is what we did yesterday, but it was kind of cloudy for us. Marin, can you tell us what you did?
We do
The chi-inv, so this is inside of Excel, equals chi-inv, and then you open a left parenthesis. What happens when you open a left parenthesis? Can we all report what we get in Excel? Equals chi-inv. What do we get prompted for? A probability. What probability do we put in? 0.05, okay? So that's our criterion alpha level, okay? We want to know where this cut point is. 5% that way, 95% that way, okay? And what's the other thing we get prompted for? Degrees of freedom. And this particular question, we had a yes, there goes, Brittany's got it, she's putting up one. We had a yes possibility and no possibility. That's two possibilities, 2 minus 1 is 1. We had 1 degree of freedom. First, how many people are okay with equals chi-inv 0.05 comma 1? Who's seeing where all that comes from, okay? Now remember what we said a couple days ago. Once you put that information in the chi-inv, it spits out the critical value, and that critical value, according to Jenna and according to Marin, was 3.84. How many people can corroborate that number inside of Excel now? Looks like a greater number of hands. We'll come there in just a moment, okay? And what did we actually, we have to get some number greater than 3.84. The critical value of the stat in this case was 3.84. What was our observed value? Can you yell it out? Our critical value was 3.84. What did we observe about 4 minutes ago inside of SPSS? 71. Is 71 greater than 3.84? All right, so now we're out here. If we're playing the game according to chi-square, we could have instead played the game according to alpha levels, and then we'd have to have an alpha level less than 0.05, and that would be something like 0.001 is what we got in the alpha level. Okay? All right, I'm not sure who I promised first. I think Hannah had a question first, and then we'll go to Jenna.
I was just confused about why you used 0.05 instead of 0.001.
Okay, good. Let's talk a little bit about that. What I'd like us all to be very familiar with is something that I have written here and something that I have written here. If you can get this down today, and we've actually talked about it before, but if you can really nail it today, you'll set the stage for great clarity the rest of the semester. Okay? We're going to be talking about two different alpha levels here. One is the criterion alpha level, and that will be 0.05 all semester long and probably in all other sciences that you ever deal with. That's our criterion alpha level. Okay? Then what we have is the observed alpha level. That'll depend on the particular data set. Today, we used a data set that was your NESI data. Right? That was what we had found from the folks over in student development. We looked at a particular variable, and we came up with an observed alpha level. As somebody correctly mentioned, it's called SIG inside of SPSS, and that level was 0, 0, 0. We can say that that's less than 0.001, so to speak. Okay? So reject HO if the observed alpha level is less than 0.05. The 0, 0, 0 was less than 0.05, and we're rejecting HO. Let me see if that works for us. Okay? All right, I'm gonna stay with your question just for a moment. There's another similarity over here because there's two different ways of playing this game. Just like we had a criterion alpha level and an observed alpha level, we have a critical, or if you like to think of it as a criterion value of the stat, and we have an observed value of the stat. Okay, the critical value of the stat in this particular case, Marin correctly told us was 3.84, and Jenna corroborated that number. That came out of chi-inv. So what has to happen here is we reject HO if the observed stat is greater than the critical value. This was 3.84, and now we're out here at 71.11. Okay? First, show of hands, how many people are following that? Okay? This is another way of saying that. And I'm going to do this one more time. I'm going to do it now in z-scores. Let's say that we're going to pretend that a particular IQ is so high that we'll say that's significantly different from the mean. What we could say is that an IQ of 100 and we'll say 30 would be 1 standard deviation, 2 standard deviations above the mean. We'll say that that's going to be significantly different from the mean. What we're basically saying is an IQ of 130 is significantly different from an IQ of 100. We're saying that a z-score of 2 is significantly different from that of 0. And we're saying that the 98th percentile is different from the 50th percentile. Those are 3 different ways of saying exactly the same thing. I can do it in percentiles, 98th percentile versus 50th. That's the first way. I can do it in z-scores, second versus 0. I can do it in raw IQ scores, 130 versus 100. Okay? Lots of different ways of talking about the same number. Those were z's. Let's throw the z out. Let's throw in a chi-square. Right? I can have a chi-square that's a certain level out here to the right. Okay? And I'd need to get out to 3.84 in this particular case in order to have significance. I got all the way out to 71. If we were to flip that around and talk about percentile ranks, I would be in something like less than the, I'd be out in the 99.999 percentile. Only a fraction of a percentage point would be to the right of me, further out that way. Okay. A couple of other hands I think went up, and we'll go with Jenna first and then to Meg.
So in Excel, obviously we can say the same thing with these two different things. We can look at rejecting if the observed level is less than 0.05 or rejecting if the observed stat is greater than the critical.
Perfect.
Do you have a preference as to which one we report?
Yeah. So typically this is what the APA will ask. They will ask that you give the name of the statistic. Are we talking about a z? Are we talking about a chi? Later on today we could have been talking about a t. We'll learn about some other ones. So which statistic did you use? Okay. Which degrees of freedom, so they know, of that family, which particular one. Okay. And then they ask you to report the actual statistic, which would be the one on that side. But they also ask you to report the particular p-value, and that's given here. So they actually want a little bit of everything in APA style. I didn't make that one up. The Denison Slate department didn't make that. That comes to us from APA. And by the way, this is actually fairly standard across all sciences, so it wouldn't just be the science of psychology.
I didn't see them on the practice sheet for the
Yes, right.
square of independence. I didn't see that.
Okay.
What I saw was in this case, reject
Yes.
the hypothesis because
That's right.
the critical value is greater than whatever. So do you want us to articulate it in terms of the critical value and below it articulate it in terms of
Yeah, I'll tell you which one we'll need on the test, really right on the test. What I like about putting it out in a sentence is it makes you put this idea into your own words. So we're going to reject the null hypothesis, and we're doing that because. So you wouldn't normally do that in an APA-style report, but for our own purposes here, so we get some idea of how do we know when we reject and when we retain. It helps to put it in sentence form. In an APA-style report, formally this would be the format, and you wouldn't need the sentence. But I thought that this is our first run at hypothesis testing, so I put the sentences in. Okay?
Okay.
All right?
So you'll tell us which one you want.
Yep, that's right. Okay, really good. A couple of other questions. I think Meg had a question or a comment.
For the three that you just said, like the 98 versus 50 percentile, that's like the percentile way of saying it. The second, the 2 versus 0, that's the z-score.
Huh?
That's the z-score. And then the 130 versus 100 is the chi-score.
What was the raw score in IQs? Okay, I was using a IQ example there. Okay, right. So some of the different stats that we could have, we can always have a raw score. That might be like an IQ score. It might be your height. It might be your weight. It might be your SAT score. Those would be the raw scores. Meg, here are some of the different kinds of stats that we're going to learn. We've already done a z. We're finishing up the chi-square. We could start, and we might start in a few minutes, the t, but that won't be on tomorrow's test. Then we've done some work with the r, but we haven't done hypothesis testing with the r. Later on, we'll learn an f. But they all work roughly the same way. There's one of those stats down here, and we always talk about some critical value that we have to exceed, and there's a corresponding percentile rank. And the cutoff percentile rank is always going to be this 0.05 alpha level. Okay, that never changes. Okay? The critical value, unfortunately, does hop around depending on the degrees of freedom. It also hops around depending on which particular stat we're using. So we have to use Excel to pull that thing out. Yeah, so there's lots of different ways of describing the same data set, the same data point that we might have on that distribution. Okay, some other questions or comments? All right, people okay with what each of these things will mean? We're telling the audience which statistic we used, which particular distribution of that statistic, how many people we had, what did we observe in terms of the statistic, and what was the probability of getting that just by chance, the probability of a type 1 error. Okay? That's actually a fairly concise yet informative statement. All right, I think the whole gang is there. Yeah, please.
I have a question.
Sure.
Is there a z-score practice sheet that we can practice on?
I don't know if you have a z-score practice sheet. I don't think I put one together. I can tell you this, though. I'm happy to do this with you right now. You can keep up that diagram that we had a moment ago. That diagram was here. Okay, that's the guy. And you remember we did a lot of exercises on this. We did equals norms in, for example, and you get prompted for a probability, which is like a percentile rank. If we put in 0.5, that would be the 50th percentile. And that would give you a 0 z-score. So we had, on a few different days listed up here, norms in takes in a probability, puts out a z-score. Norms dist takes in a z-score, puts out a probability. We had done that a while back, okay? And I think that chart is obvious enough that we probably wouldn't need, okay, an Excel spreadsheet. But thank you for the question. Other questions? All right, looks like we're maybe all set for the test tomorrow. So why don't we do this? Why don't we start getting ahead of the game, and we'll talk about what we learned for yesterday's session, which was on experimental control, and today's session on experimental control. I do want to do something that's very different to get us started. You've never done anything like this before in class. I'm going to ask you to take one of these and pass. This is not a pop quiz. Okay? This is not a pop quiz, but if you'll take one and pass it down. I'm trying to get a feel for how it is that people are preparing for class outside of class. So on the sheet, I have 2 items that ask you, I think it's 1A and 1B, that ask you about videos. If there's an extra? Yeah, okay, thank you. So the first items, 1A and 1B, are shown here in green. And they ask about how much time you spent viewing the video for yesterday's class. Okay? And we want an honest answer there. And then how much time did you spend viewing the video for today's class? Importantly, if you'll all keep your eyes on me while I'm asking this, please do not put your name or Slater box number. I'm absolutely not interested in grading you on this. I'm trying to get a feel for what fraction of the people are watching at all or watching for only a few minutes on maybe 2 days. We'll take the most recent 2 days. And then the items in red are similar questions, but they deal with the PowerPoint lecture notes that are available on the S Drive and on Blackboard. How much time did you spend reading the PowerPoint lecture notes before you came into class yesterday and today in preparation for the class? When you're done filling in these numbers, and the numbers might be 0, that's fine, but can you please put them face down on the back table? You can shuffle them up. I'm completely disinterested in individual responses. I'm just trying to get a feel for what the group is typically doing as we're preparing for each session. So your honesty is much appreciated. Yeah.
For reading, do you mean like ahead of time before watching the video?
Yeah, so some people might look at the videos and then the PowerPoints, or looking at the PowerPoints and the how much time did you spend with the PowerPoint lecture notes is really what I'm getting at.
Does that include like watching?
Yeah, you can you can make that note if you want. Yeah, that works. But critically, I want to know how much time is going in before the session starts. I'm really trying to figure out how it is that people are preparing for class, and that's the title of this. How are people preparing? And honesty is the best policy here. There's no grade. This is not a pop quiz. No Slater boxes, no names. Okay, I think that's just about everybody. We'll see if anybody else is still writing. You don't need to generate sentences here, although you can if you want to. I wasn't looking for a long series of anything here, just looking for some numbers. Is that everybody? I think we've got everybody. Okay. Well, I'll leave it back there in case anybody's not finished and they want to put theirs in anonymously somewhere in the middle of the deck. Okay. why don't we do this? Why don't we go to the PowerPoint for yesterday? This is experimental control. This is titled 1014. And hopefully people watched the video and thought about this, this bit. And so what I'd like to do is have you just take a look at some of the different issues here. And we'll ask you to maybe reflect on and share with the group the two things that I ask at the end of every video, what was particularly clear and what was less clear. And I insist that we start on what is clear first, so we get some ideas about what people find to be clear in this presentation. So we'll let you look over that, and in a minute we'll see if you can remind yourself of what was clear here and what was less clear. This is 1014, experimental control. Okay, why don't we see, anybody want to, okay, Natalie's got something. Can we go with what's clear first, Natalie?
The block randomization.
Block randomization was very clear, okay? Yeah, that's a really helpful tool, whether we're using an independent samples design or later on we'll be talking about within subject design. Natalie, can you just tell us a little bit about block randomization?
Sure. So it's like a procedure for randomly assigning participants into an experimental group and another one is an observation group.
Okay, okay.
Yeah, so it ensures that there's an equal amount of people in all of the groups.
Okay, right. So it ensures that there's an equal number of folks in all of our groups, and we have that problem of maybe having too many people in one group and not enough in another if we use just regular randomization. So block randomization gets us around that problem. Does anybody want to remind us why we have the possibility of having too many folks in one group and not enough in another if we use regular randomization? What did we mention about that? Thank you, Mira.
Because like true random numbers with strings of things would be like 6 heads in a row.
Exactly, and I think Jenna had her hand up also on that. Is that what you were going to say? So that idea was that if it's purely random, then the numbers are independent from each other, and you can get these long, long strings. You can get 9 heads in a row or 9 tails in a row, and if you have a small number of participants, you really don't want to have that kind of mismatching going on, right? So block randomization, as Natalie's pointing out, ensures that we have equal numbers in the various conditions, and that's a really nice feature, okay? All right, so that turned out to be fairly clear for you. Okay, I wonder if we can go with one other thing that was clear, and then we'll take a couple of things that were less clear. Anybody else find something particularly clear in the 1014 videos / PowerPoint / readings? Okay, thanks, Meg.
Like three conditions need to make a causal.
Thank you. I was going to do a pop quiz today, but I thought maybe I won't do one. And if I were to have done one, it would have been that question. So what she found particularly clear was this issue about the pop quiz question. I'll make it really large here. And there were 3 of them, 3 different pop quiz questions, but she picked up on the first one. Here they are. Okay? And the one I would have asked you if I had it to say was, identify the 3 conditions needed to make a causal inference. I think the answer to that question might be one of the most important responses that we can get in this entire course. If I had a small list of things that I hope you would remember several years out from this course, the answer to this would be among them. Can you help us out with any of those? Because in the video I actually do answer this one question, right? Okay.
Well, I really like the book's like example of like hitting your head, like when you get a headache. So like the covariation on that, it's like when you like when one changes, like the action of hitting your head, like the other also must change. So
Okay.
then, like you change from not having a headache to having a headache.
Okay. Okay.
So like you presume that the cause of hitting your head must occur before and then the time order.
Okay.
You had to hit your head before you got a headache.
Okay.
And then for the elimination of plausible alternative causes, you have to like rule out that like you didn't have a headache before something else could have caused it.
Okay, right. So those are the 3 ideas. We have to have covariation, we have to have a time-order relationship, and we have to be able to eliminate plausible alternative explanations. And the head-banging example is a good way of thinking about that. I want to see another hand go up, maybe on this topic. Okay, anybody want to add anything more to this? So she thought that was quite clear. Identify the 3 conditions needed to make a causal inference. Okay. All right, really good. Why don't we take one or two items that you thought were not so clear? And I always prefer, it always helps me when I hear the question phrased in such a way that this wasn't clear because, right? Because then it suggests that you actually watched the video, and after having done the reading and or watched the video, it still remained unclear, right? Yeah, please go ahead.
Well, the second part of this question,
Okay.
on like, I didn't really know how to explain it fully. Like, I know like that they're like related in the like sense that like it's about like the independent variable and like, everything, like how they're relevant.
Okay.
So I don't know like, how to explain it.
Okay, so Meg's question is really related to the second potential pop quiz question, and we'll just read that here. In your own words, explain how confounding variables are relevant to the issue of internal validity. Okay, anybody want to get us started on that? Okay, we'll go with Jenna, thanks.
Well, internal validity has to do with the idea that you're actually measuring what you intend to measure.
Good.
And so a confounding variable could be like a third variable that co-varies with the dependent variable, just like maybe your other independent variable. So then that confuses like what is actually being measured or like what is causing an effect.
Yeah. Very, very nicely stated. Okay, very, very nicely stated. So we have to think about this third variable possibility, and let's just remind ourselves of what we might mean when we're talking about a confounding variable. A confounding variable is a variable that systematically co-varies with the IV. It's a variable that systematically co-varies with the IV. And as Jenna's correctly pointing out, it might be the case that we have this third variable that's systematically co-varying with the IV, and then we do see a change in the dependent variable, but now it's not clear what's causing that. Is it this third nuisance variable that we call the confounding variable, or was it the IV? Was it some combination of the two? And internal validity is all about measuring what we want to measure. So, maybe we're wanting to measure the hittability of differently colored baseballs, but maybe we have some third variable that is systematically co-varying with our independent variable, which is the ball color, and we're not sure if the changes that we're seeing in the dependent variable are owing to the IV, which is the variable that we're interested in, or this nuisance variable, this confounding variable that's co-varying with that. So it actually is in some way relatable to the earlier question. Meg correctly told us that if we want to get a causal inference, basically, if we want to measure what we think we're measuring, we have to have a covariation, we have to have time-order relationship, we have to eliminate plausible alternative possibilities. And we're not eliminating plausible alternative possibilities if we have confounding variables. Those are very good candidates as alternative possibilities, okay, because they're systematically varying with our IV. Okay. Very good question. Okay, why don't we do this? We have a moment or two. Let's see, how much time do we have? Let's just see if we can now go over to in our last 2 minutes, we'll go over to the 1015 bit. There's the independent samples t-test. We have lots of stuff here. We'll go to the view, I'll put it in slide sorter, and I'll give you a break. I'll let you not have to report what was so clear about this, but maybe we can have you report what was less clear. Maybe there was a burning question or two that we can take in the last couple of minutes that we have here of class. So you've already watched this video. Some of the topics here were t-tests in general, one sample t-tests, two sample t-tests, two tailed tests. These were some of the varieties that we had in our video. Anybody have something that was not so clear? Okay, thank you, Jenna.
Let's see. It's the slide it's under the one sample t-test. I know there's a couple of those, but the bottom says the mean difference of 0.092 is not significantly different from the null hypothesis. When the null hypothesis is true, then the 95% confidence interval contains 0.
Yeah, okay. Okay, very good, very good. Really good question. So here we're doing the one sample t-test, and just to set the stage for that, we're comparing a value of 22.79 to our test value of 22.7. Okay, So that's the comparison that's being made, and it turns out that those two numbers are not significantly different from each other. And the critical piece here for our purposes would be to look at the sig value and get to 0.526. If we had another couple of minutes, I would say more about confidence intervals, because you picked up on it. The 95% confidence interval is not clearly described here so much, so I can understand why that might have been confusing. Of course, you won't be responsible for that anytime soon, but later this semester we'll come back to confidence intervals, and we'll probably come back to this slide. So good of you to pick that one up. Hopefully, I'll ask you this, though. Is it clear that those two numbers were not different from each other, and that was given by the sig value? Right? So they were not significantly different. OK, great. Well, thank you for your questions. I look forward to tomorrow's quiz. I'm sure you're jazzed about that as I am. And I'll look forward to seeing you in class tomorrow. Have a great day. And thank you all for your honest responses on the back table. Appreciate that.
Yeah, the check.